Good morning. Today, I'd like to talk about a very strange phenomenon. To try to understand this a little bit better, I'm going to adopt units where time is measured in years, distance is in light years, and as we saw in a previous video, one Earth gravity worth of acceleration corresponds to the number a being approximately 1. So I'll take the a to be 1 here. For a moment, I'm going to revert back to the Newtonian picture of things. Time is absolute. Space is absolute. There's none of this time dilation or length contraction or any of that stuff going on. Fred starts at the origin and travels out along the positive x-axis with acceleration a equal 1. Using Newtonian ideas, the speed is the acceleration times the time, which in this case will just be t. The x-coordinate of Fred is 1/2 acceleration times squared, which will be 1/2 t squared. Even before we do anything else, it's worth mentioning that in the Newtonian situation, the speed can be made as large as you want to make it. When t is larger than 1, the speed will be larger than the speed of light. At some positive time value, t sub e, e is for emit photon, a photon is sent off to the right from the origin. The amount of time that the photon has been traveling will be t minus t sub e, where t has to be bigger than t sub e, which is bigger than 0. Since the speed of light is 1 in the units that we're using, the x-coordinate of the photon is just going to be described by the absolute universal time minus the time that it was emitted at. A natural question to ask is, where, or equivalently, when does the photon catch up with Fred? When is 1/2 t squared and t minus t sub e equal to each other? This will give us an equation to solve. Before we start working on it, I want to be very clear on something. We start this situation at t equals 0. All relevant things that happen will have t being 0 or larger. In this equation, if I get solutions where t is not positive or 0, then that t is physically meaningless to me, even though it may solve the equation. This is a difference between the mathematics and the physics of the situation. To solve the indicated equation is just a matter of elementary algebra. The solution, though, has a couple of interesting features to it. If the quantity under the radical sign is negative, there are no real numbers t that will make this happen. It's not difficult to see that this is going to occur when the time of photon emission is bigger than 1/2 year in this case. This means that the photons being emitted from the origin, for a while at least, will be received by Fred, but there's going to be a very sharp, decisive moment when that's no longer the case. If you think about it, that's not terribly surprising. In Newtonian physics, Fred's speed will continue to increase indefinitely. Eventually, Fred will be moving faster than the speed of light, and a photon from the Newtonian picture sent towards him from behind will never catch up with him because Fred is moving faster. So point number one is not terribly surprising. You do have to think, though, what's Fred going to think about all of this? From Fred's perspective, there's going to come a moment in time where his friend at the origin suddenly winks out of existence because light from the person at the origin can no longer catch up with Fred. If Fred didn't know any better, he might be very sad and think, oh, something terrible has happened to my friend at the origin. It's almost like he's crossed some sort of horizon or the other. But of course, that's just a silly thought. The second point is weirder. If rather than T emission being bigger than a half, if it's less than one half, the quantity under the radical sign will be positive, and I'll end up with two solutions. At first glance, it's tempting to think that, well, one of these is unphysical in the way that we mentioned just a few moments ago, but that's not the case. This points out that the Newtonian observations would be very weird all by themselves. Let me explain. Early in the motion, Fred will not be moving very fast at all yet. He'll be moving much slower than the speed of light. So a photon, or electromagnetic waves emitted from the origin at such a time, will quickly catch up with Fred, and Fred will observe them. Then the electromagnetic waves head off to the right. If Fred were moving at constant speed, or moving slower than light always, that would be the end of the observation of Fred's encounter with this wave front. But that's not what's going on. In the Newtonian picture, Fred's speed increases indefinitely. Eventually, he's going faster than light. Eventually, he's going a lot faster than light. So even though the wave front may have propagated out some more, eventually Fred catches up to that wave front and sees it again. Then, because Fred's speed is continuing to increase, he moves out in front of that wave front and never sees that one again. Looking at this from the point of view of what Fred is going to see with his eyes is a very strange picture. I'm not going to discuss that, but if you want some very entertaining thinking, think about what Fred would see with a telescope or a pair of binoculars if he were looking back towards the origin as all of this is going on. Returning to special relativity, we've figured out formulas for Fred's x-coordinate in terms of both proper time and coordinate time. The acceleration number, a, is 1. The formula for Fred's position as measured by the x-coordinate in terms of a variable t reduces down to this equation. Also, at a certain moment of coordinate time, t sub b, the photon is emitted along the positive x-axis. The speed of light being 1 tells me that my previous formula for the position of the photon is still valid. Not to insult anyone's intelligence, but do a bunch of college algebra. Notice that when you square both sides of an equation, you could introduce extraneous roots, so we'll have to be careful about that. Multiplying everything out, there's a term equal to 1 on the left and on the right, so I will subtract 1 from both sides to get rid of those terms. Also, there is a term t squared there and 1 there. We will also subtract t squared away and cancel them out. Rearranging a little bit, 2 times the number that I'm looking for times 1 minus the time of photon emission needs to equal 2 times the time of emission minus the square of the time of emission. Before proceeding, it's worth mentioning something. Even assuming that nothing goes wrong with the algebra and I can solve this, this is a linear equation for t, so there are not going to be 2 solutions. This is pretty much what you would expect because Fred in the relativistic scenario never goes faster than light. The other thing is, I want to divide through in this equation by 2 multiplied by 1 minus the time of emission. There's only one situation in which that could cause me trouble. What if t sub e were equal to 1?
What? Niet. But no. I'm calling capital one. Nunca. The answer's always no.
The equation in question then reduces down to 0 equals 1, and no matter what the value of t is, this equation is never true. If time of emission equals 1, there is no t value where the photon catches up with Fred. I can certainly divide by 2 times 1 minus te as long as te isn't 1. This makes me think that other than that one odd moment, the photon will always catch up with Fred sooner or later, but we've got to be careful. We started at t equals 0. T emit has to be bigger than 0. And the t at which Fred receives the photon has to be bigger than 0, and we have done a whole bunch of algebraic manipulations. We may have introduced some extraneous roots or solutions here. So I want to be very careful about this. I want to check under what circumstances this number is positive. Firing up GNU Plot, which is my favorite plotting software, we can see that before you get to time emit equals 1, you do get solutions, and the y-coordinates are positive. So the time at which the photon catches up with Fred is positive. Everything is as it should be. As you approach t equal 1 from below, though, the time becomes indefinitely big. For t's that are larger than 1, firstly, you do get a solution, but secondly, it's extraneous. We don't want our time value to be negative. That's physically meaningless to us. So the question, at what positive time value does the photon catch up with Fred? For a while, there's a nice answer. A certain positive amount of time has passed. After a while, though, there's a solution to the equation, but it's negative. That means that the answer to the question, at what positive time does the photon catch up with Fred, is never. Fred, even in the special relativity case, has outrun photons. If you have a photon that is sent out from the origin at t equal 2, it will never reach Fred according to the O network, which is the one that's easy to think about, the inertial frame, the one that's not accelerating. This is very peculiar, but it is the result of our calculations. We're going to return to our friend Fred, who's doing the acceleration at some later point, but right now, it's finally time to start saying the T word. We'll do that in the next video. Until then, I hope everybody has a good day. I'll talk to you again soon.